look at some of the stuff. Let's look at some of the stuff that comes off the sun. Again, this is a relatively quiet sun, but it's not quiet at all. And this is during one of the solar peaks when there's lots of sunspot activity. And you notice there's some in the northern hemisphere up here, and there's some in the southern hemisphere. And here in this photograph, there was one sunspot cycle, and it's almost on the solar equator. And that all happened in just a 3-year period.
What are those actually images of? Magnetic activity, or?
These are, I mean, I don't know in detail what was happening in that month in 1999, but these are probably solar flares and individual sunspots as well. And there's coronal holes here. These dark areas are cool areas. These are coronal holes. There's a coronal hole here in this quiet period.
We get the radiation also from the coronal hole. No?
Yeah, well, it turns out the coronal hole is an area where all kinds of particles can escape from the sun.
Okay.
Well, I think what he's asking, is that in the visible spectrum, or is that in certain energy?
It's in all kinds of spectrum.
Oh, it's a broad.
It's a broad spectrum, and I don't know what the spectrum of this was, but you can see that it's different. I don't know what this, but scientists image the sun in all kinds of different wavelengths, and they see different objects at different parts of the spectrum, not necessarily the visible spectrum. And then there's this thing called the solar wind. And the solar wind is particles. It's not electromagnetic, so it's traveling more slowly, and it carries heavy objects, ions, electrons, and neutrons. It takes about 3 or 4 days to get from the sun to us. The solar wind has kind of a background level of particles that are just routinely flowing from the sun, and then during particularly active periods, the sun boils off more ions, electrons, and neutrons than it normally does, and it sends them to Earth very rapidly. And the amount is billions of tons per second. Pretty minor amount of explosive material from the sun, equivalent to probably 100,000 Hiroshima atomic bombs continuously. So it's during quiet periods, the solar wind doesn't bother the Earth very much, and I'll show you a diagram that shows that. And during more energetic times, it can cause blackouts. And this is taken during an eclipse, and you can see solar flare activity. So the sun is behind the moon in this photograph. So this is kind of what the solar wind looks like. It travels in, sorry, this is the Earth. This is the Earth. So what's happening here is the solar wind is coming towards the Earth here, and the Earth's magnetic field deflects a lot of the activity away from the Earth. And then there's a tail of the magnetic field of the Earth on the dark side. You notice on the sunlit side, so the sun's over here. On the solar side, the magnetic field of the Earth is compressed by the solar wind, and on the night side, it gets pushed way out from the Earth. And this is one of these coronal mass ejections, a CME, and compare the size of the ejection of billions of tons of solar material to the Earth. Is the Earth. And there's one of these coronal mass ejections. And here's what it looks like compared to the sun. And it's right on the limb. So this would be directed away from the Earth, not towards the Earth. So it's all about magnetic activity on the sun. These are tangles of magnetic activity that cause these sunspots to occur and eruptions to happen. And they happen all through the sunspot cycle, but it's a lot more complex and energetic during periods of high solar activity. These are coronal holes. And so when you hear about a coronal hole, if you had a telescope that could safely look at the sun, it's these dark areas here. So these are low-density regions that allow mostly X-rays to escape the sun. And if these X-rays hit the Earth, it causes problems with HF propagation. And these coronal holes can happen throughout the solar cycle, even at the bottom. But they're more common and more energetic at the top of the cycle. And the solar wind mostly originates from coronal holes. So there's a video of solar flares.
That will ionize the ionosphere?
Well, the ionosphere is mostly ionized by ultraviolet light.
Okay.
And the most energetic ultraviolet light occurs from sunspots. So this stuff is mostly the stuff we don't want to see.
Oh.
This is what causes geomagnetic storms. And I'll describe that in a little bit. So these were taken from spacecraft, just massive, and you can see what happens is when it escapes the sun, it blows up and all that material gets directed throughout space. The Earth is this tiny little dot, but some of it hits us, but the vast majority misses the Earth. Only the tiniest amount hits the Earth.
What's the time frame on the picture on the left?
Well, you can see it here, so it looks like it's about 4 hours it looks like.
Oh, okay.
Watch that. I'm not sure if that's hours or minutes. I honestly don't know.
Okay.
Could be minutes, yeah. But it's at least 5 minutes, and it could be several hours. I suspect it's minutes. So it starts at 08 and runs through 11. So that might be 4 or 5 minutes, and I think that's kind of what it is.
Minutes from the
Yeah.
right hand.
Okay. So solar flares are this extremely hot gas, and the nasty thing about it that it contains something called energetic protons. They have a tremendous amount of energy, and if they get pulled into the Earth's atmosphere, it causes terrible things, and I'll show you that in a little bit. Solar flares also carry very large amounts of X-ray radiation, and that appears at the Earth in only 8 minutes, very fast. It's very rare at this part of the sunspot cycle, but at the top of the sunspot cycle, there are things, some people call them radio blackouts, where all the bands go completely dead. The scientific name is an ionospheric disturbance, sudden ionospheric disturbance, SID. A lot of hands call them radio blackouts. Has anybody experienced one of those?
Oh, yeah.
Tell me what your experience was.
It was March 1989. I had to go out to the grocery store to get something. I left my radio on. I was on 30-meter band, and at that time, BBC was still on. It was blasting in. Okay, I come back 10 minutes later, and like everything was dead. I turned all around. I called a little handprint who had a silent key, and I asked him, he told me he had this idea. It was like 15 minutes.
Yep.
And it lasted for hours.
Yeah, and so your experience is just like mine. They happen suddenly,
Yeah.
and they last 2 or 3 hours, but the bands come back to the way they were. Gradually, it happens suddenly, like somebody flipped a
I
switch.
thought something was wrong with my antenna.
Yep. A lot of people try to debug their radios, but they happen suddenly, and after 3 or 4 hours, the bands are just like they were before it happened. But then 2 or 3 days later, you get the energetic particles, and everything goes to hell, and can stay pretty bad for a few days. So that's a solar flare. Sudden ionospheric disturbances can only happen in the daytime. Where we live on the Earth has to be able to see the sun. Otherwise, it wouldn't affect us. So if anybody ever tells you they experience an SID at night, they're wrong. Can't happen. But in the daytime, it does. There are all kinds of different flares. The most most energetic ones are called X flares. We're not going to see any of those anymore, but the scientists classify them in all kinds of different ways. The weaker ones are going to continue. X flares we're probably not going to see anymore, but I can only say probably. Coronal mass ejections, this is when billions of tons per second of energetic particles are launched from the sun. They're still happening at this part of the sunspot cycle, and if we happen to be in the place where they hit the Earth, it causes really bad effects on propagation. And here's a video showing a CME, all that material, billions of tons leaving the sun. And there's a little timer on it too. I can't quite see it. And all of this material is magnetically charged.
Will the particles eventually reach Earth and become part of Earth?
Yes, some of them will become part of our atmosphere.
Okay.
But the vast majority won't. Remember, compared to the sun, compared to all of the space around the sun, the Earth it's a pinprick compared to all this space. So the vast majority of this stuff never gets to the Earth. And most of it that gets to the Earth gets pushed away. I'll show you that. So here's a little detail about the size of space weather storms. That refers to solar flares and CMEs. This is a good time to describe this. All of these materials coming from the sun have magnetic fields, powerful magnetic fields associated with it. It comes from a plasma on the sun. And the Earth's magnetic, so here's the Earth here. The Earth's magnetic field is northward pointing. If the interplanetary magnetic field, the magnetic field associated with all this stuff coming from the sun, does anybody remember from elementary school experiments with magnets? Remember that? So if magnets had, if you put the north pole of the magnet against the north pole of the other magnet, you couldn't push them together, right?
You had the two skies.
But if you turn it the other way, they hit. So this is showing what happens when these magnetic particles and X-rays from the sun are of the opposite magnetic polarity of the Earth. And what happens is it gets sucked into the high latitudes of the sun and cause things like auroras. If the planetary magnetic field is the other way, remember those magnets from elementary school, the Earth is able to push all that stuff away. It gets pushed away from the Earth and never gets in. So the polarity of the interplanetary magnetic field is a big deal. The ham radio guys don't like to see it this way because that means the bands are going to be dead. The guys that like to watch auroras love it because it means the sky is going to be bright red. So I just said all that stuff about the orientation of the interplanetary magnetic field.